Yes, wow, Dennis. Okay. I think you can score a full mark, right? Because I think you got a lot of time, right? To to do the test too. Okay. I think it's quite easiest compared to instrumentation test too. I agree, right? Okay, for today, will be the last chapter, okay, um, for this subject, and then I hope that the following weeks, um, we will do some revision about the exam, okay, all right. Um, let's go to finish up this chapter, okay. Okay, are you ready, guys? All right. Okay. So controller design. You have learned this chapter last week. Okay. So in the controller design, so what do we have? Uh, for the traditional one, we will have the PID. Okay. So P, that's mean professional. That's mean you only adjust the KP. And I is the integral, you adjust the Ki over S integral, and D you adjust the difference. Okay, right. Um, so there are each of them have their own function, right? Their own purpose. For example, the KP, you can get it. So we want to get the it's depending on our performance, so whether we want to get the steady state error. All right, we want to get it almost equal to zero, and you can look about the rise time. Okay, so KP can make the rise time going faster, and about the settling time. All right, and what else? Settling time, the error. What else? I'm also forgot about it. I'm getting old already. Okay. Anyone? What is this? Okay. Hmm. Anyway, we that. All right. So if you look at one graph here, and this is what are we going to achieve? Okay. Uh, for example, our input, our reference is the step input. So this is the overshoot. So when you adjust the KP, you put it too large, so you will got it. The rise time will be faster, okay. And however, the overshoot will be larger, okay. And of course, the test error you will also got it is will be quite larger also. And then after that, you combine with the integral, you will see that you can minimize a little bit the overshoot. I think it will affect a little bit, but the most important thing is the steady state error. So you can get it is a zero. Okay, and however, the rise time it will be a little bit slower, and also the time constant. So we have looked the time constant between the integral and the professional. So the time constant will be slower than time constant Ki. I put it Ki. So for the time constant Kp, okay, and then that's why after that you need d derivative. So derivative will minimize your overshoot. Okay, that one, right? And normally we combine Kp, Ki, and also Kd. Right? Okay. So I think you still remember that. Okay. And we have done this one when we apply the P only, Kp. So we try to find what is the Kp, what is the K value for damping ratio equal to 0.707. Then we need to do some root locus there. Okay, right, and then after that you can get the K value. That K value we produce the damping ratio for 0.707. And then from the information of the K value for the damping ratio, you can get the what we call it, the roots of at the K value, and then the roots will tell you the performance of the system in terms of time constant, the what we call it, the natural frequency, and dam frequency. Okay. Um, and then we use the I integral only. So what you will see that you will do again the root locus and so on. Yeah, this is like your test two, right? Keep going there and there. Okay. And then you also find the K value and the roots, and then you compare. This one you only use the integral, and this one you only use the professional. So you will look into that, the time constant, right? The integral will be a little bit slower, okay, with the compared to the professional. So in the last topic, last example, which is 6.3. So we're going to do this. Okay. Um, Now, what happens if you combine between professional and integral? Okay. For control system shown below, design a PI controller so that steady state error is eliminated. So we know that when we apply the integral, we can eliminate the steady state error, but the transient characteristic of P controller is maintained. Okay, and then the damping ratio is equal to 0.707. All right. Okay, so if you look into the block diagram there, so you got the gain controller here. Now you apply P and I here, so that's mean P is Kp and Ki is K over S here. Okay, so if we want to make it, we want to simplify it, so we got it Kps plus Ki over S here. And then you can bring the Kp outside, then S plus Ki over Kp here over S. Okay. Alright. Then let's make Ki over Kp a one value. For example, I put it Z. Okay, zeros there, where your Z is equal to Ki over Kp. Okay. Alright. In this case, we will try to find what is the value of the Ki, what is the value of Kp, so that we can achieve for the damping ratio equal to 0.707. Okay, that is our objective. Ah, okay. Then after that, you will do the what we call it, the root locus again. So first step, you need to find the open loop transfer function. Open loop transfer function, which is the K, G, and H here. Your K is the gain, okay, Kp S plus Z S, and your G is the process. So if you look at there, 1 over S plus 1, S plus 2 here, and then what do we got it here? We got it is Kp S plus Z divided with S plus 1 and also S plus 2 here. So this is your KGH, because in order to get the root local, so you need to find the overload transfer function first. Okay, so if you look into that, okay, I forgot to put that S here. If you look into that, there are 3 poles there. So I can put it here. That is the step during the root local. Pole is equal to 0, minus 1, and also minus 2. And you got it the Z, alright? So here, okay. So maybe I can put it as 0.5, okay, alright. Why I put it 0.5? Okay, you can look at this one. Okay, right. This is the value of your pole, right? 0. And this one is minus 1. This one is minus 2. This is the pole, right? So where are you going to put the what we call it? Sorry, this is going to be minus. Okay. So why you choose 0.5? Actually, you can choose 0.1, 0.2, 0.3, as long right is minus. Why? Because the 0, it will be located at this point, right? Okay. You cannot put your 0 at this point. If you put a 0 at this point, that means your root local will going to this one, to this direction. That means your system will be not stable. We don't want to do that. We want to get our system will be stable, right? So if you do like this, so that means your what we call it, your pole going to this direction, right? The root locus, okay. Another one we going to this direction, okay. Right. So this one is equal to 0 minus 0.5. Okay. This part, do you understand about it? This one. Okay. Our objective, we want to find the Ki and Kp here. However, we got it Z here, 0.5. Okay. So you can choose any value that you want. Yes, correct. Any value from minus 1 to 0. Yeah. Okay. Okay, good. So, next. So, you will do again the root locus. You will plot, and you will find the number of asymptote, and then the asymptote angle. Um, okay, and then the asymptote centroid. So where the asymptote and breakaway. So in this case, we will have the breakaway because these two pole, right? Okay, together, and then this mean the locus will be like this one and this one. Okay, right. And then in order to find the breakaway point, so you need to find the dk over ds. So from the characteristic equation, 1 plus kgh equal to 0. Your kgh right here, blah, 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 blah. And then you need to solve it by using, wow, this formula. and after that you got it the three value there, S1 and also S2 and S3, right? So the logic one is S1 because the value that we lie on the real axis minus 1.45. Okay, and then if you intersection, so you don't see any intersections there. Why? Because your asymptote angle will be what is the 1.25. Okay, the asymptote angle will be 90 degree and also 270 degree. Okay, here. Alright. Okay, so you don't have any intersection to the imaginary axis, and then after that you will this is your root locus is about. Okay, I think that the part of root locus, I think you already familiar about it, right? Because it stay fresh in your mind, right? Got that just two. Okay, then you got it your root locus something like this one. Okay, and then uh, okay, and then from your damping ratio, so you can get it the beta here. Okay, so beta um, the damping ratio equal to cos beta, so beta equal to inverse and 0.707. Then you got it at 45 degree, so you can draw the 45 degree from here. You can straight away draw it. Then you got it this point. Then what is it? This point is minus 1.33 plus with 1.33j here. Okay, so this is the information that we can get it from here. Oh, alright, sorry. So what else that we can get it from here is one over t, and then this one you got it this here, so this one is 1.33. This one is represent the d. Okay, and omega n equal to 1.33 also, so you can get the omega n here, 1.88, so 1 over t. Okay, we represent the 133, so you can get your t here is 0.75. Okay, so this is what you got it here. Okay, all right. The most important thing is to find the what we call it the k, right? Is here. K is here. So you need to connected this one. Okay. So this one need to minus with this one, right? Minus this one, minus this one, and also this one. Okay. So coming back with your open loop transfer function. Where is it? I'm going to do. Okay, no mind. We do it again. 1 plus kgh equal to 0. So 1 plus modulus kgh here equal to 0. Minus 1, then put the modulus here. kgh is your value for k s plus z here, and s plus 1, s plus 2 equal to 1. So because you want to find the k value, so that's mean your k, this value I put it is a, you need to minus it, so that's mean minus and minus z here, divided with the k a minus with 0 there, and a minus with minus 1, and a minus with minus 2 equal to 1. Okay, right. Actually it will be plus lah, a plus z. Okay, so this one you put it the a. So what is the a? So a is means that this value lah. Okay, okay, then we got it here. We find it the k here, and now is equal to 2.44. Okay, 2.44. Right. So this is the value of the k that you can adjust it, and in order to find this ki over kp here is equal to 0.5, right, equal to z. So k is here is the kp, then you got it, your ki is equal to 1.22. Okay, all right. So that's mean if we choose the kp equal to 2.44, okay, so that's mean your ki is equal to 1.22, right? So ki divided with 2.44, right, equal to 0.5. So this one, all right? Okay. All right, that's mean if you choose the different value, for example, you choose 0.3 minus 0.3, so the answer will be difference. Okay, right? However, why the answer will be different? Yeah, of course, you got the difference value for the roots. However, our target is we going to achieve the density ratio equal to 0.70. As long that we can achieve this one, so it doesn't matter what is the value that you got it. Okay. Now, this part clear. Do you have any question? Okay. Yeah. Okay. Good. Alright. So I think this part, I think you already know about it. You already know. Okay. Alright. Any question? Ada persoalan lagi? Any? No? Okay. Right. Let's look what the performance that we can get it if we combine T and I there. So we got it from the information from this root. We got a time constant, and then omega n 1.88 and so on, right? And omega d, okay, 1.33. So if you look into the time constant there, so before this, if we adjust the kp only, we got it the time constant is equal to 0.67, right? And if we only put it the integral, so we got it is 1. What is it? The integral? Yeah, 2.62. Okay. So if you look into that, the fastest time response is when you only put the proportional. Okay. All right. So we discussed about the time constant 0.67. This one the fast will be the fastest one. However, the steady state error is there. The steady state error is not equal to 0. Okay. And then if we only use the integral, right, of course we can get the steady state error equal to 0. However, the time constant will be quite slower, right, compared to proportional. Okay, right, that is what we're going to discuss, right? So now we combine between Kp and Ki here, then we can achieve the time constant. It will be more faster than you apply the integral only, right? But it will be a little bit slower compared to the professional. Okay, so if you can accept this one in your system, all right, so yeah, we can go for it. Okay, all right. So this in this example, it shows that yep, this is what happened when you apply Kp and Ki there. So you can achieve the steady state error, of course, equal to 0. And then the time constant, yep, the, okay, so lah, you can get it. Okay, you can accept it 0.75. Okay, all right. Okay, I think that's it for this subject. We have finished. Uh, Covers all the topic. Okay. Done. Alright. Any question? Clear? We're done. Persoalan ke? Or still sleepy? Okay. Alright. Okay, before we end our class, I just want to share a little bit, right? Okay, this one done. We have done this one. Okay, good. Uh, Okay, so we have learned chapter 6 is the control system, right? Is the basic one that combine between the root locus and so on. Okay. Um, chapter 5 is about Nyquist diagram, right? Para plot. So you have been done that one before. So that means it, it will not be asked for the exam, the Nyquist diagram, right? Not anymore. And about the board plot, right? Okay. Uh, then we also have learned the root locus stability, right? And chapter 3, first order and second order. Okay. Right. First order. Second order is not been asked before, right? So maybe it will ask for the exam. Okay. All right. Which part is quite difficult for you? Nyquist or board plot or root locus? Just want to ask you which part that is difficult for you. Root locus, Nyquist diagram, board plot, or control design. Root locus drawing code, sir. Okay. Board plot, yeah. Okay. Anyone agree that board plot chapter will be difficult compared to others? So there are three things that you need to draw, right? Root locus and Nyquist. Partially agree. Wow, tennis, good. And then board plot, right? So there are three things: root locus, Nyquist, and board plot. Nyquist will not be asked, right? The root locus, yes, we will still use there. Okay. So everybody agree that board plot is quite difficult, right, to draw, because you need to use the uh, what we call it, the approximate asymptote, right? Asymptote guideline like this. Anyone? No answer. Okay. Or you just online there. So board plot will be difficult, right? Yoo-hoo! Hey, tennis. Okay, good. So, do you want to know there is what is the easiest one in order to draw the board plot? Nak tahu tak? Sebenarnya nak draw board plot ni senang je. You don't need to use this what we call it, this asymptote, this approximate asymptote, right? Okay, there are this one very easiest. Okay, let's look. All right. Okay. All right. We coming back to there. This one. All right. So, if you draw the board plot, right? So you need to do. Yeah. Let's go back to this one. You are given the transfer function like this one. Then you need to compute the opposite transfer function kgh, and then you need to identify the asymptote. So you got a k, and then you got it this one, what you call it, 1 plus ts. Okay, and then after that this one is 1 over s, and 1 plus ts, 1 plus ts, and so on. Okay, so that means there are 5 asymptotes that you need to draw first, and then after that you start approximate from the asymptote, right? Okay, so this one is quite difficult to do that, right? Because some of you doesn't understand uh, what I'm have drawing that time, right? So minus 40, and then after that 0 plus minus 40 dB per decade. So this one we go to minus 40 dB per decade, and then after that need to plus 20. Oh, what is it all about? Okay, that is will be the easiest one. Okay, right. So let's do this. Okay, we have do this before. Okay, example. Where is my? Okay, where is my? Okay, let's going back to example 5.0 here. Okay, for a system shown below, draw the board diagram for k equal to 1. From the board diagram, obtain the gain and phase margin, estimate the critical value of k for stability. Alright, so first step, of course, this part you cannot avoid, opposite transfer function, kgh. Then you got it, k is 1, and then 20, then you time with s plus 0.8 there, divided with s squared, s plus 2, and s plus 8 there. And then if you simplify this one, you will got it is here. Okay. So kgh go to 1. Yeah, you can delay. Okay, this one we got it, this part. Okay, if you simplify it, so you got it is 1 plus 1.25s divided with s squared, 1 plus 0.5s, and then 1 plus 0.125s here. Okay, right. So this one you got it after you simplified it. Okay, all right, and then I put it, this one is gs here. Then you can find lah this one as equal to jw, jw here. Okay, then you can get it 1 plus j 1.25 jw divided with minus square plus 1.j 0.5 w 1 plus 0.5 25 kW. Okay, right. Okay, and then for the phase shift, that what we got, minus 80 degree minus inverse tangent 0.5 omega minus with inverse tangent 0.125 omega plus inverse tangent 1.25 omega then. Okay, right. So this part is doesn't matter. Okay, right. This part it doesn't matter, but most important thing is this one. Okay, this one. Right. So let's look. What can you do after this? Okay. So before this, we need to identify. Okay, there are 1, 2, 3, 4. 4 asymptote there, but this one is quite difficult to draw, right? Using the asymptote. Okay, so right now we apply on what we have done in Nyquist diagram before. Okay, so quite simple. So you just take it, the GS here, right? So KGS is represent the GS here is 20 S plus 0.8 here divided with S squared, S plus 2 and S plus 8. Okay, right? Then this one, right? So you can use your calculator. AI plus 0.8 AI squared AI plus 2 and AI plus 8. Okay, so what you're going to do is you need to find the omega, and also you need to find the gain. Okay, and this one you need to find the pi, and this one you need to find pi 0. So last topic for the Nyquist diagram, you only find the what is it? The gain and also the pi area, right? So this one you will plot in your Nyquist diagram, right? Okay, betul kan? Okay, so in both plot, what you need to do, you need to find the another one is dB equal to 20 log gain. That is what I'm going to describe about. Betul kan? Because the both plot is plotted is based on gain, based on 20 log gain. Okay, so you need to find this one only. Okay, betul. Senang kan? Macam you dah belajar. Okay, right now, what is this value? This value is depending on your GS here, 20S plus 0.8. Yeah, this one. And this one, and of course this one. Okay, so omega we start from 0 to infinity, right? So 0.8 here is will be, this is your guideline 0.8 and 8 and also 2 up, 2 will be located at here. Okay, again 0.8 2 and 8. So you can get another value, for example 0.5 0.3 0.1 here, 0.8, maybe you can get it 1 2 3 and 5, so this one 10, right? Then you can start to use your calculator. Okay, use your calculator to get it. I think you already know how to use the calculator, right? Kan? Dah tahu kan? Macam mana nak guna calculator kan? To apply AI plus this one, this one, this one, this one, right? Betul? Yeah, okay. Then, for example, you use your calculator, your gain, you got it is 100.6. Okay, for 0.1, for 0.3, you got it is 11.7, blah, 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 blah. And then for the base angle, you got it is minus 176, minus 170, then base real, minus 176. Maintain for the negative. For the positive, so you need to minus with 360, right? So this one, for example, positive, you need to 178.2 minus with 360. Okay. Now, you already got it this one, and you gain this one. On the Nike diagram, you just need gain and also real, right? The phase angle real. However, for the boat plot, you need to do again one more thing, 20 log 100.6. Okay, right? So what you can do is 20 log, put the unknown value is A. Okay, put the unknown value is A. Let me clear it. So you just put it 20 log, so alpha A, right? And then you just press the calculate. Okay, so what is A? Put it 100.6. Now you got it, the value is 40. Alright, and then 11.7 is 21.4. Okay, alright, so you got all this value. Okay, this one you already got it. This one, so in order to plot the boat plot, you just need to use this value and also this value. Okay, so go into your boat plot. So let's see. So you just need to make the scale 0, 20, 40, and 60, and you just plot. Oh, the first one for 0.1. Okay, 0.1 there, 0.1 equal to 40.1. Yeah, plot it. Simple, right? Kan? It's simple, right? So you don't need to use the approximate asymptote. Macam mana? Okay, happy? Guys, faham tak faham ni? Do you understand? Okay. So that means senang kan? So you don't need to draw the asymptote, draw this one. No need. So you just plot straight away. You will got the same value, 40.1 here. Yeah, this is your first point. And then at 0.3, if you look at 0.3, okay, this one 0.1, 0.2, 0.3. So it will go to, let's look. It will go to, yeah, almost 21. Yeah, here, 21. Okay. Okay, you got another two point there. Then after that, 13.1 for 0.5, 0.5 here. Yeah, you got it 13 here. So you can draw straight to here. Okay, so you plot your point, all the point there, you plot it, then you will draw the book plot, right? Draw straight, or maybe go into this trade, into this. Okay, So here we got your board plot easily, okay, easily compared to the asymptote. And then same thing happened to the phase angle. First one is minus 176. Yeah, 176 here. Minus 170, 175 here, 176. Yep, and okay, 1. Then we go to 170 for 0 0.3. 0 0.3 here. Okay, we go to 170. Maybe this one is not accurate yet. Right? So 170, we go there. Yeah. Boom. Okay. 0 0.5, we go to 165. 165 here. 165. Yep. Yeah, you big guesses. So we go to this. Okay. Now, how about that? How about that? Do. Okay. Alright. So this is what happened when you plotted all these values. Okay. Yep. 40, 21.1, 30.2. Okay. Alright. So this is the easiest method compared to the what we call it, the approximate asymptote. Okay. Macam mana? Senang? Boleh faham? Alright. So which one is easiest one? Okay, senang. Okay, good. Alright. So now you don't have any issue about the board plot anymore, right? Because it's same with the what we call it, the Nyquist diagram before. Okay. However, this method, um, if you don't get the value correctly, that's mean you will lose the total mark at this section. Okay. All right. Okay. If you can get all this value correctly, so that's mean, yep, you will got this the mark on this value. Okay. However, my what you call it, my suggestion, right? So you just need to write also this value for the JW, right? And then you got this equation and this equation. Okay. So why I want you to write this equation also. Maybe you can use your calculator again. You use your calculator again to write this equation, and then you can double check. You put the W equal to 0.5. Then you double check again that you got this value. Right? You got this value. You got the same value, so that you don't do the careless mistake. Okay. So please check this one. Okay. Alright, and before this, in order to find the guideline, so we use this one, 1 plus 1.25 s, and then this one is represent the t, 1.25, then you got it, the omega is 1 over t, then you got it back, 0.8 actually. Okay, so you can skip this one, okay, and then you can straight away use this value as your guideline. Okay, this value as your guideline. However, need to be bear in your mind. So this one need to be s plus something. S plus something. All right. It's not 1 plus 1.25 s. Okay. Right. If you get the equation is start from like this one. Okay. Then you straight away take this one, so it will be wrong. Okay, it need to be s plus something, right? S, only s, it doesn't have the coefficient there, right? S plus something, then you can straight away take this value as your guideline on this table. Okay, that's it for the board plot. I think it'd be the easiest one. Okay, are you happy? Dah. Alright. So there are two methods there. Um, whether you want to use the approximate board plot or you can just use straight away to use this value. Okay. Alright. Do you have any question? Ada apa-apa lagi soalan? Do you have any question? Senang eh? Okay. Test one result is ready. Yup, the test one result is ready. I just got it yesterday, and then I need to compile again for the mark from question one and question two from other lecturer. So I will let you know by next week on Thursday. Okay. Uh, sure you can get a full mark, right? Test one and test two, right? Okay. Any question? No? Okay. In that case, I think that's it for our class. So I will see you again on Thursday. Is it okay? Because we don't have we already covered all this the topic. Okay. Alright. Okay. Alright. Good. So I will see you again on Thursday. Okay. Inshallah. Alright. In this case, okay. That's it. Thank you for your attendance. Alright. Bye bye. Okay, and good afternoon. Okay, bye bye.